Hi all. Today I am going to discuss about the topic heap sort. What is heap? Heap is a special tree-based data structure that satisfies the following special heap properties. Shape property. Heap data structure is always a complete binary tree, which means all levels of the tree are fully filled. Heap property. All nodes are either greater than or equal to or less than or equal to each of its children. If the parent nodes are greater than the child nodes, heap is called a max heap, and if the parent nodes are smaller than the child nodes, heap is called a min heap. Complete binary tree. A complete binary tree is a binary tree in which all the levels are completely filled except possibly the lowest one, which is filled from the left. In a complete binary tree, all the levels of a tree are filled entirely except the last level. In the last level, nodes might or might not be fully filled. Also, let's note that all the nodes should be filled from the left. Given is an example of a complete binary tree. A binary heap. A binary heap is a complete binary tree in which every node satisfies the heap property. These are the max heap property and the min heap property. It states that if B is a child of A, then key of A greater than or equal to key of A. This implies that the elements at every node will be either greater than or equal to the element at its left or right child. Thus, the root node has the highest key value in the heap. Such a heap is commonly known as a max heap. Elements at every node will be either less than or equal to the element of its left and right child. Thus, the root has the lowest key value. Such a heap is called a min heap. Given in the slides are the example of a min heap and a max heap. Heap types. Max heaps, or largest element at root, have the max heap property. That is, for all nodes I, excluding the root, A of parent of I greater than or equal to A of I. In min heaps, or the smallest element of the root, have the min heap property. That is, for all nodes I, excluding the root, A of parent of I less than or equal to A of I. Heap property. In min heap, first element is the smallest. So, we want to sort a list in ascending order. We create a min heap from that list and pick the first element as it is the smallest. Then we repeat the process with remaining elements. In max heap, the first element is the largest. Hence, it is used when we need to sort the list in descending order. Heap data structure. A heap is a nearly complete binary tree with the following two properties. Structural property. All levels are full except possibly the last one, which is filled from left to right. Order or heap property. For any node x, parent of x greater than or equal to x. From the heap property, it follows that the root is the maximum element of the heap. Array representation of heaps. A heap can be stored as an array A, as given in the following figure. So according to the figure, root of the tree is A of 1. That is a value on the first position, which is 16. Next, left child of A of I equal to A of 2I. Here A of I 1 equal to A of 2I, that is 2 into 1, 2. So the left child will be the value in the second position, that is 40. In the same way, right child of A of I equal to A of 2I plus 1. Parent of A of I equal to A of I by 2. Heap size of A less than or equal to length of A. The elements in the subarray A of n by 2 plus 1 up to n are the leaves. Operations on heaps. The three main operations that are happening on the heaps are max heapify. Here we maintain or restore the max heap property. Second one is build max heap, in which we create a max heap from an unordered array. Next, the third one is heap sort, in which we sort an array in place. Now let's look how to insert a new element in a binary heap. Consider a max heap H with n elements. Inserting the new value to the heap is done in the following two steps. Add the new value at the bottom of H in such a way that H is still a complete binary tree but not necessarily a heap. Let the new value rise to its appropriate place in H so that H now becomes a heap as well. To do this, compare the new value with its parent to check if they are the correct order. If they are, then the procedure halts. Else, the new value and its parent's value are swapped and step 2 is repeated. Let us consider an example. Consider a max heap and insert 30 in it. This is the given binary heap. So after inserting 30, the binary heap will be like this. So after inserting 30, we have to heapify the binary tree. At first, we have to compare the inserted value, that is 30, with its parent value 12. So here 30 is greater than 12, so it violates the max heap property. So we have to interchange 30 and 12. After interchanging, we have to compare 30 with its parent value, that is 20. Next value 20. So here also there is a violation of max heap property. Hence we have to interchange 30 and 20. So after heapifying, the binary tree will be converted to max heap. Consider another example. Build a max heap from the given set of numbers 45, 36, 54, 27, 63, 72, 61 and 80. Here now heap is given, just set of numbers are given. So we have to insert the elements one by one and form a max heap. This is also another way of inserting elements in a binary heap. So in the step 1, we are inserting the first element 45. Step 2, we are inserting second element 36. When we insert a new element, we have to compare the parent element in order to see if there is any violation of the max heap property. If there is a violation of max heap property, we have to rectify it by swapping the values. Step 3, when we insert the next value 54, there's a violation of max heap property. So we have to swap the elements 54 and 45. Only after rectifying the max heap property, we can add the next element. So the next element to be added is 27. There is no violation. So next we can add 63. When we add 63, there is a violation when we compare with its parent 36. So we have to swap 63 and 36. Then we have to compare 63 with its parent 54 in step 7. So there is a violation. So to swap 63 and 54. In step 8 and step 9, there is no violation, the max heap property. In step 10, there is a violation. So we have to rectify it by swapping the values 45 and 72. Now in step 11, we have 72 became the root by swapping the value 63 and 72. So in step 12 and step 13, when we enter the new elements, there is no valuation, hence the max heap is built. Now we can look how to build a heap. Convert an array A of 1 to n into max heap n equal to length of A. The elements in the subarray A of n by 2 plus 1 up to n are the leaves. Apply max heapify on elements between 1 and n by 2. The algorithm for building max heap is given. First step is n equal to length of A. Second step for I equal to n by 2 down to n. Third step, do max heapify of A comma n. Let us consider an example and look how to build a heap. So there is an array elements 4, 1, 3, 2, 16, 9, 10, 14, 8 and 7. So in the previous slide, we have seen that the algorithm of building a max heap of array A. So here we are considering a heap size that is A of length, and we are doing a for loop that is for I equal to A of length by 2 down to 1. So here when we look at the elements, there are 10 elements in the array. So when we divide the length of the array elements, that is 10 divided by 2, then the value will be 5. So we have to start from the iteration 5 to 1. So the heap rooted at the vertex or array index 5 is already a max heap. So no change is made. In the figure B, the heap rooted at index 4 is not a max heap. The value 2 is smaller than its children. We restore the max heap property by swapping 2 with the larger child key 40. If we have swapped it with 8, it would not be a max heap. This is why we always swap the larger child. In the figure C, we can see the result after swapping the values 2 with the larger key 40. So when we look at the value, the figure C, we are decrementing the value of I to 3. There is another violation of max heap property, and we swap the value 3 at index 3 with the value 10 at the index 7. In figure D, the heap at index 2 violates the max heap property. We must propagate the value 1 down by swapping with 60 and then with 7 in a recursive code to max heapify. In the figure E, finally checking the value at index I, value 4 against its children, we find we need to swap it with the value 16 at index 2 and then with the value 14 at index 4 and value 8 at index 9 in 2 recursive codes to max heapify. Then after doing these steps, the figure F shows the resulting max heap. So now we can see the algorithm to insert an element in a max heap. So these are the steps to insert an element in a max heap. It is given in the form of an algorithm. These steps depict the steps I have discussed through the examples. So according to the algorithm, we assume that H with n elements is stored in array heap. VAL or val has to be inserted in the heap. POS stands for position. PAR stands for location of the parent of val. Note that this algorithm inserts a single value in the heap. So the complexity of this algorithm is big O log n. This is because a binary heap has big O log n length. Now we can look how to delete an element from a binary heap. Consider a max heap H having n elements. An element is always deleted from the root of the heap. So, deleting an element from the heap is done in the following 3 steps. Replace the root node's value with the last node's value so that H is still a complete binary tree but not necessarily a heap. Delete the last node. Sink down the new root node's value so that H satisfies the heap property. In this step, interchange the root node's value with its child node's value, whichever is the largest amongst its children. Let us demonstrate the deletion of an element from a max heap with the help of an example. Consider the given max heap. In the given example, we have to delete the root node 90 and from the max heap. And we have to swap the root. In order to do that, we have to swap the root node 90 with the last node 75 max. Now we have to delete the last node. Here the last node is 90. After deleting node with the value 90 from heap, max heap is as follows. Now we have to compare root node 75 with its left child 89. Here root value 75 is smaller than its left child value 89. So compare the left child 89 with its right sibling 70. Here left child value 89 is larger than its right sibling 70. So swap the root 75 with the left child 89. Now again we compare 75 with the left child 36. Here node with the value 75 is larger than its left child. So we compare the node 75 with its right child 85. Here node with the value 75 is smaller than the right child 85. So we swap both of them. After swapping, the max heap is as follows. Now compare the node with value 75 with its left child 50. Node with value 75 is larger than its left child 50 and it does not have the right child. So we stop the process. Finally, max heap after deleting the root node 90 is as follows. We can look at the algorithm to delete the root element in a max heap. So these are the steps of algorithm to delete the root element in a max heap. So this steps depicts the steps I have discussed in the previous example. Here we assume that heap H with n elements is stored using a sequential array called heap. Last is the last element in the heap and PTR left and right denote the position of last and its left and right children respectively as it moves down the heap. So here I have discussed how to insert and delete elements in a max heap. The same step is followed in a min heap. The only difference is that the root element will have the lowest value and the children or leaves will have the higher values. Now we can discuss about heap sort. Heap sort is one of the best sorting methods that has no quadratic worst case scenarios. Heap sort is a comparison-based sorting technique based on a binary heap data structure. It is similar to selection sort, where we first find the minimum element and place the minimum element at the beginning. We repeat the same process for the remaining. Let's see how a heap sort works. Heap sort algorithm is divided into two basic parts. First, create a heap of the unsorted list or array. Then a sorted array is created by repeatedly removing the largest or smallest element from the heap and inserting it into the array. The heap is reconstructed after each removal. Now let's see the algorithm for heap sort. It is depicted in 3 steps. By looking at the algorithm, we can understand that the heap sort algorithm is a combination of insertion of heap and deletion of heap. Let us understand more about heap sort with the help of an example. Consider the following example. Suppose the array that is to be sorted contains the following elements: 11, 2, 9, 30, 57, 25, 70, 1, 90, and 3. We build the heap from the above binary tree and is shown below. So we have built the binary tree by doing the steps that has been already discussed. Now we can discuss about the sorting technique. Here we only discussed the sorting technique. Now the root 90 is moved to the last location by exchanging it with 3. Finally, 90 is eliminated from the heap by reducing the maximum index value of an array by 1. The balance elements are then rearranged into the heap. The heap and array looks like as shown in the following diagram. Similarly, when the current root 57 is exchanged with 2 and eliminated from the heap by reducing the maximum index value of the array by 1, the balance elements are then rearranged into the heap. The heap and array look like as shown in the figure. Following the same approach, the following phases are followed until the fully sorted array is achieved. So this is all about the topic of heap sort